Hello, my name is Shubham Ganar, and today I will be presenting two of my projects from my doctoral thesis titled as From Leaves to Lab, Understanding the Droplet Impact on Engineered Surfaces to Provide Insight for Efficient Agricultural Spraying. Firstly, what do you mean by the droplet impact? The droplet impact is a very fascinating phenomenon observed in nature, and it can be seen everywhere whenever it rains. The rain droplet hitting the liquid can be seen on lakes, ponds, and saturated water bodies. Similarly, the rain droplets hitting on the solid can be seen on bricks, leaves, walls, roofs, etc. Here are some of the examples of the droplet impact done in the lab to mimic the real life situations. As you can see in the slide, the droplet impact on the sand, droplet impact on the sand, liquid pools, superhydrophobic surfaces, drop-on-drop impact, drop-on flexible surfaces, and drop-on flexible cantilever beam. As you can see, the outcome of the droplet impact on different surfaces are fascinating and different from each other. This phenomena seems to be simple and fascinating, but it conveys a complex physics of fluid dynamics. Understanding this droplet impact physics can be helpful in many engineering and practical applications, such as spray coating, agricultural spraying, anti-icing coatings, and inkjet printings, etc. The physics of this droplet impact can be studied on liquid as well as on the solid surfaces. For our experiment, we focused our interest on the droplet impact on the solid surfaces. When the droplet hits the solid surfaces, it gives the following outcome. That is the full rebound with the secondary droplet, full rebound with splash, deposition, prompt splash, corona splash, partial rebound, and partial rebound with splash. All these different outcomes depends on the various parameters and dimensionless numbers. The relevant, the relevant dimensionless numbers are the Reynolds number and Weber number, where Reynolds number is inertial to the viscous forces and Weber number is inertial to the surface tension forces. Other factors such as a chemical property, that is the hydrophobicity of the surfaces, can also influence the droplet impact outcome. Similarly, the geometrical features such as macro texture, porous surfaces, micro nano features, composite surfaces can also have the effect have the effect on the droplet impact outcome. Similarly, the physical stimulus such as mechanical vibration, temperature of the surface, magnetic field around the surfaces, ultrasonic vibration can influence the droplet impact outcome. The two projects I will be explaining, the project in project one, we investigated the droplet impact dynamics on these superhydrophobic leaves, which focusing on the influence of its micro nano features on static and dynamic wettability. In the second project, we investigated the droplet impact dynamics on the liquid impregnated surfaces, which have with a varying stability, and it was infused with different oils, that is the silicon oil and hexadecan. Before starting, I would like to show you what the superhydrophobic surfaces and the allied surfaces mean. Superhydrophobic surfaces are those on which the water forms a contact angle which has a greater than 150 degrees. This is due to the presence of air layer beneath the water droplet, beneath the air layer between the water and the surfaces. For example, in the last video, you can see the lotus leaf exhibits this property, making the water droplet roll off easily. Liquid impregnated surfaces are those surfaces in which this air layer is replaced by the lubricating oil, creating a smooth and slippery interface. This allows the droplet to easily glide on these surfaces with the minimum addition. We followed a systematic methodology to perform our experiment. Firstly, the sample fabrication for the project one, that is the superhydrophobic leaves, and project two, the liquid impregnated surfaces. Next, we conducted a sample characterization using various tools such as FEACM, goniometer, etc. If the result does not matches with the previously reported literature, we repeated the fabrication process. Once the sample meet the we characteristics values, we proceed with the droplet impact experiment followed by data analysis and the validation and the modeling. So now the droplet impact on the leaves. During the monsoon season, we identified the three types of leaves in our campus that exhibits a superhydrophobic behavior. Out of curiosity, we examined their micro nano features and measured their wettability. For the wettability measurement and droplet impact, we took the raw leaves and to check the FESM images. As the FESM, it works in high vacuum, which created a distortion in the sample. To overcome this, we use a special low-cost drying method without using any chemicals, in which what we did, we took the fresh leaf, cleaned it with the DI water and the nitrogen gas, and kept it in the pressure just below the atmospheric pressure for 20 to 25 hours. After that, we check this dried leaves in FESEM, and it was observed that the micro nano features was still retained. This was because this process allowed a slow evaporation of the moisture that preserves this micro nano features. Morphology. As you can see in this image for Cassiodora in 1 microscale, you can see the ellipticular wax platelets with the sharp-edged nano features which are sparsely spaced over the surface. In ACV, you can see that the complex hierarchical topography of papilia with 3D reentrant morphology that is very closely packed to each other, and it has a shape of a mushroom-like structure on the surfaces. In the BV, in the Bohunia variegata, that is the BV, you can see at the 1 micron scale that it has a similar nano features which is present in a Cassitora, but the only difference here is these nano features are very closely packed near to each other and the distance between them is very less. That is a closely packed. Then we did the wettability measurements. This graph shows the wettability results of wettability measurement. As you can see in the first plot, that all the leaves were having a super hydrophobic property and it is super hydrophobic in nature. That is the contact angle is greater than 150 degrees. Record हो रहा है? Yes. But in the next plot, But in the next plot, the contact angle hysteresis and the roll-off angle of the Cassitora is very high when compared to two other samples. The reason behind this reason behind this high contact angle and roll-off angle is a collapse of this air pocket beneath the water layer, which eventually turns this Cassie-Baxter state into the Wenzel state. The theoretical explanation for this phenomena is explained in the next slide with the help of the thermodynamical stability. In the figure, you can see the two states, a state A in which water get infused between the two consecutive wax features, that is the Wenzel state, that there air that there is a air pocket, and in the state B, you can see the air pocket between the water and the wax, that is the Cassie-Baxter state. The interfacial energy of this state can be written as shown in the equation 1 for the figure A and the equation 2 for the figure B. To have a stable air layer and the air pocket beneath the droplet, the equation 2 must be less than equation 1. By solving this, we get the ratio that is R by 2H should be less than 0.15198, where R is the radial distance between the two wax features and H is the height of that wax features. When this RH is calculated for different leaves, we found that the Cassitora, where these nanofeatures are sparsely spaced, the water will impregnate and the air pocket will get collapsed. This increases the water surface contact area, which is responsible for high contact angle hysteresis and high roll-off angle. As you can see in the image, the densely sprayed nanofeatures at the top region and the sparsely sprayed region in the valley region. Followed by the droplet impact, you can see the droplet impact of water on these leaves at the different Faber number. In the higher for the low For the low Weber number, that is the Weber number 9, you can see the entrapment of a small air bubble in the Cassiodora. This happens because the receding speed of the water at the bottom is less as compared to the receding speed at the top layer of the droplet. It is only seen in Cassiodora at the lower Weber number. The reason behind this is again the sparsely spaced nano features. At the higher Weber number, you can see that the ejection of the smaller droplet from the rim of the droplet during the retraction phase. This is because of the Rayleigh plateau instability is get created on the periphery of the droplet, thus creating a thus creating a smaller secondary droplet from the interface. We also calculated the height of rebound from the surfaces for the Cassiodora and for different leaves. It has been found that the height of the Cassiodora at the lower Weber number is higher when compared to the Weber number at 105. This is because the due to the secondary droplet formation, the energy get used, and this results in a lower height of the rebound height. Also, we did the droplet diameter spreading analysis in which we observed that the spreading and the receding spreading of the Cassiodora was less when compared with all the leaves. We also did the droplet impact on the macro structures of Cassiodora and BV at the Weber number of 105. It has been observed that the impact on the Cassiodora microstructure divided the droplet in two parts from center, and also the contact time is less when compared to BV. There is no such division of droplet is happened. Only a secondary droplets are formed because of the Rayleigh plateau instability. This shows that the Cassiodora have a prominent macrostructure compared to BV. This was confirmed by the optical images and the theoretical explanation which was provided by the Varanasi group with the ratio of TC, that is the duration of contact time, with the tau, which is the property of the system. That is, for our case, tau is equal to 0.0061 second, and Tc is the duration of the contact of the water with the surfaces. When we plotted, it shows that the Cassiodora have the effect of micro features on the droplet impact, and ACV and BV, Baunia variegata, does not have the micro features effect on this droplet impact. We plotted the graph of Dmax to the D and compared it with the relevant previous studies. It has been found that it followed and matches the regime of Weber number to the power 1 to the power by 0.25, as you can see in this figure. For the conclusion, in this project we compared the static and dynamic wettability of these three superhydrophobic leaves with their morphologies. We also calculated their we also proved that this in terms of thermodynamic stability for this static change. We also carried out the droplet impact on the macro structures and the experiment validation. Project 2, droplet impact on LIS. First, the figure shows a schematic outline to prepare the LIS. Firstly, the fabrication of the texture surface was done using a photolithography. Second, the selection of the post spacing was done by calculating the critical contact angle method, where theta c is the critical contact angle, and it depends purely upon the surface features properties such as length, width, and post spacing, followed by the OTS functionalization and coating it with the silicon oil and hexadecan. The coating speed or the withdrawal speed was calculated by using a capillary number. As you can see, the textured surface coated with silicon oil gives a van der Waal LIS, and for hexadecan it is non-van der Waal LIS. This this will be why we are calling it van der Waals and non-van der Waals will be explaining in the consecutive slides. So the wettability measurements and the stability of the LIS. First table shows the contact angle measurements of different fluids on a smooth OTS surface for air and water environment. Second table shows the critical contact angle for the particular pore spacing, and the bottom table shows the equivalent criteria for stability which was given by the Varanasi group. From the figure, we can see that the EW1 configuration and its equivalent criteria for stability, that is the theta OSW is equal to 0, where theta OS is the contact angle of oil in solid on solid in water environment. Similarly, E similarly for air EA1, the theta OS in air environment is 0. This signifies that the silicon oil will be stable in air and water environment. Also, there will be the presence of thin oil layer above the top of the pores, as you can see in figure. Both the figure that the orange layer is a silicon, orange color is a silicon oil also present on the top of the post of the square features. Similarly, for hexadecan, it has been found that the hexadecan will be stable in air and water environment up to the pore spacing of 30 micron, and there will be no presence of thin layer on the top of the square post. We performed a theoretical calculations. We performed a theoretical calculation to verify the presence of thin film above the surface post by evaluating the effective Hammerker constant between the solid and liquid. Literature suggests that if the effective Hammerker constant is negative, then the thin film will form. While for thin film will form, for our calculation shows the silicon oil had a negative effective Hammerker constant, which shows that the thin film will form, while the hexadecan is positive, indicating no thin film formation. To further validate this, we measured the roll-off angle of water droplet on both the LIS samples. The roll-off angle was found to be higher on the hexadecan infused surfaces as the exposed top post offered the resistance to the droplet movement. In contrast, the silicon oil exhibits the lower roll-off angle due to the presence of the thin film. Due to the presence of the thin film, the microscopic observation of the textured surfaces shows that particle movement beside the post in hexadecan that there is a no thin film, whereas for silicon oil, if you can see the particles are moving above the top of the post, which suggests that there is a presence of the thin film of the silicon oil on the top of the silicon posts. So in this slide, the droplet impact on 5 micron post spacing is shown. As you can see at the lower Weber number for hexadecan LIS, the droplet have no rebound when compared with the silicon LIS. This is because during the receding phase, it does not have enough energy to overcome the resistance offered by the open top posts. Whereas the silicon oil, the droplet will rebound completely because of the presence of this thin film. For Weber number 63, the hexadecan will have a partial rebound. Still it does not have the enough energy to lift it from the droplet from the surfaces. As we increase the Weber number, you can see the full rebound in the hexadecan. As now at this Weber number, the droplet got the sufficient energy to lift off from the surfaces and to overcome the resistance offered by the surface exposed top post. As we further increase the Weber number up to 247, you can see the transition from full rebound to the no rebound. This is because the kinetic energy of the droplet replaces the oil between the two consecutive pore spacing and get water gets in that and does not allow to detach from the surfaces. Thus, the hexadecan will have no rebound at the higher Weber number. We can say that this transition from the full rebound to no rebound has a critical velocity. To find the critical velocity, we will be explaining it in the next slide. Further in this we can see that the for the silicon oil there is a formation of the secondary droplet. The secondary droplet is detached from the main primary droplet during the receding phase. This is due to the development of the Rayleigh plateau instability at the rim of the droplet. Though the droplet is get droplet secondary droplet is produced, but the primary droplet will rebound from the surface. This shows that it have a sufficient energy to lift off from the surfaces. To lift off from the surfaces. Similarly, we did the droplet impact experiment on 20 and 30 micro post spacing. Due to the time constraint, I'm not explaining this in here. So the effect of the droplet oil on the droplet impact. So in the right hand side, you can see the regime map for the different transition from partial rebound to rebound, then no rebound to the partial rebound in the hexadecan region. As for the silicon oil, there will be always rebound. For this hexadecan, we did the scaling parameter with the help of kinetic pressure and the capillary pressure, where capillary pressure is the pressure has that is the energy holding the hexadecan, that is holding the lubricant within the two consecutive spore space. By comparing, we get the critical velocity parameter for the transition from full rebound to no rebound. That is, at what velocity the water will replace the oil between the two consecutive pores. The table shows the results and it matches with our experimental results for the non-van der Waals as it have a different transitions. But for the non that is for non-van der Waals LS, but it does not matches with the van der Waals LS, that is the silicon coated textured surfaces. This is because that there is a presence of thin film, and to have this scaling law, we did not consider the presence of thin film. The extra energy is required to clear this barrier of thin film. Thus, the extra energy is required. We also plotted the graph for Dmax to the D0. It also follows the Weber number slope of Weber number to the power 0.25. Concluding this project 2, in which we did the high-speed imaging to study the droplet impact behavior on van der Waals and non-van der Waals LS, and for the different post spacing. The lubricating, we also calculate the stability of the lubricant. We also had the uh, different phases of the rebound and no rebound in this van der Waals and non-van der Waals LS, and also plotted the various plots. The project one, was published. Both of the project one and project two was published in the Physics of Fluid, and also the various conferences was poster talk was given on these projects. Other projects which I have an experience is the other projects. The in project 3, which of my thesis, I investigated the droplet impact on smooth PDMS surfaces that were either coated or absorbed separately with different lubricant, and also examined their influence in the droplet outcome influence of the softness on the droplet dynamics. Now, also, in project 4, we extended this study with the textured PDMS, where the droplet were tested on these samples coated again with silicon oil and hexadecan. As a part of my research experience, I fabricated laser textured and different superhydrophobic surfaces for studying ice and hydrate adhesion. I also performed experiment on the solid impact on the liquid pools, which have with the ball having a different wettability and size. I also did the electrowettability experiment on the smooth and textured PDMS, in which I explore how the electric field can tune the wettability of the surface. These are my following skill sets. Basically, the main question is how I can contribute in your group. I bring the expertise in droplet impact, weighting, and adhesions on different engineered surfaces. I have hand-on experience in designing and fabricating experimental setup for precise fluid and solid surface interaction studies, along with the proficiency in the advanced techniques such as high-speed imaging, FEACM, rheology, and microscopy. My strength lies in the connecting fundamental droplet physics to the real-world applications like condensation and energy system, which enables me to contribute effectively to the both fundamental research and application-driven projects in your group.